Hey physics, so what we're going to go ahead and do is take a look at an example of how to solve a problem involving angular kinematics. And so this is very similar to stuff we've done in the past with linear kinematics. So hopefully this will be helpful to you guys so you can get your 3 problems finished for today's assignment. So before we get started on the example, we're going to just do a bit of review. So yesterday's assignment was to familiarize yourself with various symbols. And yeah, this is what you saw yesterday. We have angular displacement, delta theta, which is measured in radians. And so this is just like, the idea of, rotating or twirling or whatever. So, skateboarding, you might do a 360. That's 1 rotation, okay? That would be 2 pi radians. So that's all we're talking about is how much something has rotated, okay? On the other hand, angular velocity is how quickly something is rotating. So an ice skater, for example, might end up rotating rather quickly after, say, she brings her arms and legs inward as she's spinning. She's going to end up with a very high angular velocity, and that's measured in radians per second, just like it could be measured in degrees per second, but we simply use radians. So we have both initial and final angular velocities. Alpha is angular acceleration, radians per second squared. And then we have, of course, time, delta t, which is measured in seconds. So these should be somewhat familiar to you from your lesson yesterday. And these are our symbols for angular kinematics that we're going to be using in this example. So just to compare, kinematic 1, we're familiar with it looking like this. Delta x equals 1/2 vi plus vf times delta t. And as we saw, you can make substitutions. We substitute theta in for x, and we substitute in omega I and omega f, and we would make that into an angular kinematic. We see kinematic 2 here, kinematic 3, and kinematic 4. And then as we make those substitutions, they turn into the following equations. Kinematic 1, delta theta equals 1/2 omega I plus omega f delta t. And then kinematic 2 with alpha substituted in for acceleration. Kinematic 3, kinematic 4. So it gives you an idea of, how these equations look. And of course, we're only going to be using the equations on the right. So, those are the numbers for the equations as we'll refer to them periodically, right? So let's go ahead and just remember the sort of process that we use for solving kinematic problems, which is fairly straightforward. We always begin by, of course, reading the problem very carefully, and then we make a list of variables, right? So for this, angular kinematics, your list is going to look like that. And this is, kind of like what you saw in your bell work today. So if you did that, you know what I'm talking about. And once you've made that list, then you're going to read the problem again and identify all your given information, okay? So friendly reminder, sometimes given information might have hidden pieces of information, such as the object starts from rest or it comes to a stop. That would tell you that omega I, the initial velocity, was angular velocity was 0. You're going to add your variable to your list is a question mark, so whatever it is you're solving for, you're going to put a question mark next to it. Then you're going to identify the term in the list that has nothing next to it. So it doesn't have a number because it wasn't given, and you're not solving for it, so that's what's missing, right? You're going to kind of cross that off, and then you're going to choose the equation that does not have whatever the missing term is, okay? So if I have a number next to everything except delta theta, then I'm going to have to choose the one equation that does not have delta theta in it as an example. And then, of course, you're going to do substitution and algebra to solve. So let's go ahead and apply this process to our example today. It says here we have a disk initially at rest, and it begins to accelerate at a rate of 4.5 radians per second squared, and continues until it reaches an angular displacement of 370 radians. And the question we have to answer, how long did this period of acceleration last? So if we read the problem again, we see hopefully 3 pieces of given information. Now the 2 obvious ones here are the numbers, 4.5 radians per second squared and 370 radians. And if you're not sure what those represent, then you could look at the units or you could look at the context clues from the problem itself. In this case, pretty straightforward. They tell us that it's accelerating at a rate of 4.5 radians per second squared, so that's alpha, our angular acceleration. And then we see 370 radians as our angular displacement, delta theta. And then the hidden piece of information here is in fact the fact that it starts at rest initially. So just reading that and sort of deciphering what they give us, right? So once we've done that, we're going to make our list, right? Well, we already read it again. We're going to make a list, and we're going to then sort of identify our given information, right? So what do we know? We know that the angular acceleration, 4.5 radians per second squared. We know the angular displacement is 370 radians. And as we said, it begins at rest, and therefore we know omega I is 0. And at that point, we just have to look at the question. How long did the period of acceleration last? So we're going to put our question mark next to our delta t here. And then we have omega f as our piece of missing information, right? So the missing here is omega f. In other words, we have to choose the equation that does not have omega f in it because I don't know anything about it and I can't use it, so I certainly have to pick an equation that does not have omega f. So if we're going to go ahead and do that, then what equation is that going to be? Well, let's take a look at them, right? So if you just quickly take a peek, should be pretty quickly obvious that kinematic 3 is missing omega f. It's the only one, in fact. And so now we're going to apply kinematic 3 to our problem. We have delta theta equals omega I delta t plus 1/2 alpha delta t squared. We're going to go ahead and then substitute and solve. So a little bit of algebra. 370 is delta theta, leaving off units for simplicity. Omega I was 0, so naturally anything times 0 times t is going to be 0 here. So plus 1/2, 4.5 as our acceleration, delta t squared. So do a little bit of algebra, and you get 12.8 seconds for the answer to our example problem. So we're going to go ahead and leave it here. Hopefully this made some sense to you guys. It should be very familiar to you just from what we've done in the past. And as always, I'll be available via questions. For questions via email or Google Hangouts. So feel free to message me as needed. Thanks, guys.